Do you have any questions about anything that I covered last time? Oh, okay. Last time I tried to solve a simple problem. Okay, a unique axial tension problem. Okay, the problem that we have the traction applied at both ends, and the traction are spatial in the sense that the net force that we have only one component in x3 direction, and there's no net moment for that particular tractions. Okay, to solve this problem, I start by guessing the form of the straight field. Okay, with the knowledge from strength of materials. So let's say that okay, we assume the form similar to what you learn from that class. Okay, so we just simply assume that the applied traction at both ends generate only the normal traction in x3 direction, and that normal it generate only the normal stress in x3 direction. So here we assume the tensor, straight tensor in this particular form. We have all zero components except for sigma 3 okay, equal to P over A here is the area. Okay, so once we guess the form for the straight field, we then check equilibrium condition. Okay, and we found that equilibrium equation is satisfied automatically, right? Because the straight here is constant and body force disappear. So equilibrium equation is satisfied. And also we verify Beltrami-Mitchell equation as well, because for the body force field equal to 0, so Beltrami-Mitchell equation just simply reduce to this equation. Okay, because stress that we guess is constant. Just a second, I'll be back in a minute. I get a phone call here. Sorry. Okay. We already checked Beltrami-Mitchell equation, right, for this particular case, because stress is constant. So the Laplace of sigma ij and sigma kk comma ij vanish, right? Because stress is independent of x. Okay. Is that clear? So now we can say that the straight field that we guess is compatible, and that will generate straight field that compatible. So that confirms the existence of the displacement field, right? So now for the case straight field, and we'll check the equilibrium condition and also Beltrami-Mitchell equation. So that guarantee the existence of the displacement field. So now we have all field, and we can say that all field that we got there satisfy all field equation. Okay, so it still remains to check the boundary conditions. I check the boundary condition at the side face already, right? Last time, because the body here is cylindrical body, so the unit normal vector on the side face just simply n1, n2, 0. And n1 and n2 can be any arbitrary number here, because the cross section is arbitrary, right? The shape is arbitrary, so we cannot get an n1 and n2 in any spatial form, because here I didn't specify the shape of the cross section. I just say that okay, the cross section is arbitrary. Okay, so the form of unit normal vector is simply n1, n2, and 0. It's 0. The component is 0 for the third component because the body is cylinder, right? So the cross section here, the cross section is normal to the axis of the cylinder are always identical. So that implies that n3 have to be 0. So here, so we can see easily that when we multiply the gauge straight field with the normal vector, unit normal vector, we always get 0 vector, right? So what I can say here, the gauge straight field generates 0 traction on the boundary S pi, right? So that's exactly the same as what we know on that boundary, right? Because on the surface S pi, we have the traction free condition, or we know the traction equal to 0. So this implies that the gauge straight field satisfy the boundary conditions on the surface S pi automatically. Okay. Last time I stopped here. So it still remains to verify the boundary conditions on at the left end and at the right end, right? Okay. For Saint-Venant principle, if we simply focus on the solution in the interior zone and we don't care much about the end zone, so in that particular case, forcing the boundary condition at the left and at the right end directly by looking at the traction at every point may make the problem very complicated. But in this case, I will not force the traction condition directly. So I will just simply look at the net force and net moment that generated by stress and generated by the prescribed traction. If we can verify that both of them are the same, so now we can say that the boundary condition at the left and at the right end are satisfied. Okay, so I will look at the surface SL first. How can I get the traction? How can I get the traction from the straight field? So I can get the traction easily in terms of straight components, right? As I showed you before, and then I can just simply use the formula to compute the net force in terms of the traction components, right? So this is the formula that I talk about. So if you have straight components, you look at the left end, you can just simply take the integration like this. Okay, so you can get the net forces, okay, at the left end, all the components of the net force like this. Okay. So I simply plug in components that we have in the gauge form, right, of the straight field. So we know that sigma 1, 3, sigma 2, 3 are zeros, right? But sigma 3, 3 is simply P over A. I plug it in, okay? I plug everything in, so I get something like this. And because P over A is simply a constant, so the integral of a constant over the cross-sectional area is simply P over A multiplied by the area. So the area cancel out. So now we have only P. And we have the negative side here. So you can see that this is the net forces that we get from the gauge straight field. Okay, this is not the one that prescribed, right? This is the one that generated by straight field that we gauge. So this is FL. But if you look at the condition at the left end, we also know that we look at the problem that the net force, the prescribed traction generated the generate the net forces equal to P in that direction, right? So this exactly the same as what we have here, right? So we can say that FL here is exactly the same as FL0, right? So we can do exactly the same thing for for the net moments. So we plug in components of stress that we get before, plug it in this formula. So now we can get the net moments generated by the stress field that we get. So sigma 3 is constant. Okay, we can plug it in here. Okay, and sigma 2 3 and sigma 1 3 are 0, right? So the last component disappear. Okay, so now we get something like this, right? So we plug it in and we use the fact that POA is constant. So I just simply move it out of the integral, right? So now I can conclude what? So if you remember, I choose the origin of the coordinate system at the centroid of the cross section. So that will imply what? So the integral here is 0, right? Because the origin is at the centroid. So the integral here is 0. So the integral here is 0. So is that clear to you? If you go back to look at the definition of the centroid, if the origin is at the centroid, what does it mean? So x1 bar and x2 bar have to be 0, right? The location or the distance from the origin to the centroid of the cross section is 0. So this term have to be 0, right? If you understand or you remember the definition of the centroid, so this can be obtained easily, right? So now we get 0, 0, 0, right? So we get 0 net moments for the stress field that we guessed. So this is what we have. That what I mentioned before, that we have to get the net force and moments, and then we have to confirm with the one that prescribed. Okay, so you can see because the problem that we are interested in here, we specify the traction that generated only the traction, the net force only in the x3 direction, and here at the left end, P pointing in the negative x3 direction. So it's exactly the same as what we have here. So now I can say that FL is simply F0L. Okay. Also, ML is exactly the same as M0L because for the prescribed traction that we look at here, it generates 0 moments, right? So this is exactly the same as what we got from the stress field. Okay, so now I can say that the gas stress field satisfy the net force and net moment conditions. Okay, at the left end. Okay. Is there any question about anything here? So you can see that I didn't try to force the traction condition at every point at the left end, but I look in terms of the net forces and net moments, right? And I try to check the thing that I got from stress and those from specified traction. If the net forces and net moments are the same, now I can say that the boundary condition at the left end is approximately satisfied. Okay, so satisfying these conditions, we cannot conclude that the traction are satisfied at every point. Okay, so we just simply satisfy the condition in an average sense. Okay, we can do exactly the same in the same way for the surface SR. Okay, the condition at the right end can be checked in the same way. So first we have to compute the net forces and moments at the right end. So we do exactly in the same way. I just simply took the formula that I showed you before for the right end. So you have to be careful about the sign that appear in those formula. So then I just simply plug in the component of the gauge straight field into this formula and then perform the integration. So we know that sigma 1, 3 and sigma 2, 3 are 0. So the first component and the second component just disappear. And the last one here, so we plug in sigma 3, 3 to POA. So now, because POA is constant, so that integral simply reduced to P, right? So I will get this. The same thing for the moment. Okay, I plug in sigma 2, 3 and sigma 1, 3 equal to 0. So that term 0. Okay, that term is 0. So the whole thing here disappear. Okay, and sigma 3, 3 is simply a constant, right? I move from I move outside the integral. So the thing inside is simply like this. So and then I enforce the condition from the fact that the origin is at the centroid. So the integral of the coordinate x1, x2 disappears. So that term is 0. That term is 0. So the whole thing here is 0. So I get 0 net moments due to the gauge straight field. So here I can conclude that the net forces and net moments are satisfied, right? That condition are satisfied at the right end. So here I can say that the boundary condition on the surface SR is satisfied. Okay. So now I'm done with verifying all boundary conditions. On the surface S pi, we check the traction at every point. We already verified that the traction is satisfied. The traction conditions are satisfied at every point on the surface S pi. At the left and at the right ends, so we verify the net forces and moments, right? And we see that they are satisfied as well. Okay, if we look at the simplified boundary value problem, we can say that we got the solution already, right? So the straight field that we guessed at the beginning satisfy all the conditions. Okay. So now I conclude that this one is the solution of the problem, right? Because it satisfies equilibrium equation, it satisfies compatibility condition, it satisfies boundary condition on the surface S pi, satisfy the simplified boundary condition on the surface SL. The simplified boundary condition in this sense, I just simply means that the net forces and net moments are satisfied, not the traction individually. Okay, so we satisfy the net force and moment condition at the left end. The same thing happened to the right end. So the simplified boundary conditions are satisfied. So now we check all the conditions for the gauge straight field and all the conditions are satisfied. So now I can say that the gauge straight field here is the solution of the simplified boundary value problem. I would like to emphasize here that this is the solution of the simplified boundary value problem, not the exact or the original boundary value problem, because here we didn't look at the traction at any point on the cross section. So I will say that okay, the straight that I got here is the solution of the simplified BVP. Okay, so if you just simply look at the solution in the interior zone here, now you can say that the straight field that you got here is simply what you want, right? But if you move back to the zone close to the end, so the one that you got here may not be okay, right? Because we didn't check the boundary condition in terms of the traction at every point. So we cannot expect that straight field here is the solution of the problem, or is the exact solution of the problem for the whole boundary, for the whole body. Okay, so we just simply use the Saint-Vernon principle to conclude that if we don't care much about the detail of the traction at both ends, so this should be the appropriate solution in the interior zone. It doesn't matter how you distribute the traction at both ends, but if they have the net forces and moments like what I show you here, so this is the appropriate solution at the interior zone. Okay, that's what I can conclude. Now, if you want to get strain field, now you can get easily, right? Because you know stress, so now you can generate strain field based on strain relationship. Okay, you just simply plug in stress that you got before into this, plug that in this formula. So now you can get strain. So this is the stress that we got. So this is the final strain. Okay, and for the displacement field, we can get it from the integration of strain displacement relationship, right? We don't need to worry about the integration, because we confirmed before that straight field that we get satisfy Beltrami-Michel equation. So that implies that strain field that you got before is compatible, right? So once strain field is compatible, so this equation can be integrated to get the displacement field. Or I can say that the equation here is integrable. Okay, so I perform the integration. I can get the displacement field of this particular form. So the process of integration, I think you learned it from the homework assignment, right? I think that, okay, you should be able to do this. It will take time, because in integration of all equation that are available here, okay, to get the final form like this, so you have to to get several conditions, and finally you end up with this displacement field. So I separate the displacement field into two parts. The first part that is unique is the part that generated the strain field that's non-zero. Okay, so that is the unique part of the displacement field, the one that generates non-zero strain. And the second part here is a part that generates the zero strain, or the part associated with rigid body motion. Okay, for this particular problem, we don't have any point on the boundary that we constrain against the movement, right? So we can say that this body can experience rigid body motion without changing any strain and strain field inside. You can imagine that, okay, you apply the force at both ends and you hold it like that, and you walk around. Okay, you hold the body and you apply it at both ends and hold the body like that, and you walk around. So in that case, you can see that any point in the body can move, right, rigidly. So in that case, we can say that the displacement is not unique, because we can always add this part to the displacement field without changing strain and strain field that you have before. Okay, and we don't have a way to get the constant B and C here, because we don't have displacement boundary conditions. Okay, so we have to leave the answer like this. But if you don't care about the rigid body motion, you care only the displacement part that generate non-zero strain, so you can drop that term if you want to. Okay, because that one will not generate any straight field. Okay, is that clear to you? Okay. I have a remark here. So if we look at the traction generated by stress that we got before, if we would like to know what kind of traction that we have to apply at both ends, okay, what kind of traction that we have to apply at both ends, and the stress field that we got here is the exact solution at every point. Okay, so now if we look at the traction generated by the stress field that we got before, so we just simply look at the left end. So we multiply the stress field by the normal traction. Okay, and sorry, normal vector at the left end, which is 0, 0, -1. So we get the traction like this. So this is the traction that generated by stress that we got. Okay. At the right end, we can do exactly in the same way. So this is the traction generated by the stress field at the right end. We get the traction like this. So you can see that the traction generated by stress that we got before is simply a constant. Okay, it's simply a normal pressure acting at the left and at the right end with a constant value, right? So what does it mean? Okay, so if you look at this special form of the traction, this is the one that generated by the solution that we got before. So this imply what? Imply what? So if the traction, the prescribed traction, the one that you apply at the left end and at the right end, are exactly the same as the TL and TR here that you got from straight field, what can you conclude? If T0L is exactly the same as that one, and T0R is exactly the same as that one, what can you conclude? Now you can conclude that the solution of the simplified and the original BVP are exactly the same. Is that right? If the traction you prescribe at both ends, T0L and T0R, are exactly the same as the one that you got from the straight field. Okay. Now you can say that the traction condition at both ends are satisfied at every point. So that implies what? Straight field that you got before is simply the exact solution of the problem. Is that right? Is that right? Do you have any question about anything here? No? Okay. Just a second. Okay. So if you don't have any question, I will move to the second problem. Okay. Now we look at different type of traction applied at the left and at the right ends. Let's say that, okay, we look at, again, the cylindrical body, and the cross section is arbitrary. Okay. And look at the traction T0L at the left end. We applied some kind of traction at the left end that generate the net forces and moment like this. Let's say that the traction that we apply at the left end generate zero net force like this. Okay, but we have non-zero moment about x2 axis. So this is the net moment that I talk about. Okay, we can apply any kind of traction that can generate the net forces moment like this. Okay, you can think about one kind of distribution. For example, the bending stress, the traction that generated from the bending stress for the beam case. You learn from beam theory, right? If you apply the bending stress at the left end like that, okay, that will generate zero net force, right, at the cross section. Okay, and for the moment, so the distribution of the bending stress will generate a moment, bending moment. Okay, I didn't put any specific form of T0L because T0L that can generate this kind of net forces moment are not unique, right? There are several types of the distribution that can generate the same net force and moment like this. Okay, for example, one of the distribution I can think about. Sorry, one of the distribution that I can think about is the linear distribution like this. So if we apply the normal traction like this, okay, we have the tensile stress and compressive stress, and the distribution is linear like this. This is the one that you are familiar with, right? When you learn how to calculate stress in beam at the cross section of the beam in beam theory. So you know the distribution of the stress across the section like this. So if we look at the distribution like that, you compute the net force, you will get zero. And when you compute the net moment, you're going to get the bending moment at the cross section. This is one example that can generate the net force and moments like this, but it's not the only one that's possible. You can think about that again. If you look at stress that distribute like this, it may not be linear. Let's say that this is non-linear somehow, like this. Okay, let's say that the part that we have compressive stress and tensile stress are symmetric somehow with respect to the cross section that you have, because the cross section here is quite arbitrary. So you may have the chip of the centroid, the neutral axis here. So let's say that okay, we have the distribution like this. So when you do the calculation of the net forces, you may end up with zero. But the distribution here is not exactly the same as that one. So what I try to tell you here, there are several types of distribution that may end up with the same net force moments like this. Okay. Also at the right end, I apply the traction. Okay, T0R. I apply the traction with the net forces moment like this. Okay, or I just have the bending moment about positive x2 direction for the right end. Okay, this is the problem that we try to solve here. Okay, so if you don't care much about the distribution at any point, okay, at the left end and at the right end, so we just look at in terms of the net force moment. So this problem, I just simply apply loading at the left and at the right end. The loading that I consider here is simply the bending moment, right? I apply the bending moment at both ends. I can say in that way. If I didn't look at the way that the traction distributed at any point, we look in terms of the net force and moment. So this is the one that I apply. Okay, at the left end, I apply the bending moment about the negative x2 direction, and at the right end, I apply the same value of bending moment, but in opposite direction. Okay, so this problem we call the pure bending problem, because the loading that we apply at the left and at the right end are simply bending moments. No net forces right? At the left and at the right end. Okay. Is that clear to you about the problem that we focus on here? Okay. Now, I would like to get the solution inside. Okay, because the moment that I look at here can be generated from infinite number of tractions. There are several types of traction that can generate this moment. Okay, so now the distribution of the traction at the left and at the right end will affect to the solution only at the end based on the Saint-Bernard principle. Okay, if you change the type of the distribution but fixed the value of m, the solution will change in the region near the end zones. But the solution inside here, we can say that the solution here is approximately constant. I shouldn't say constant. It approximately the same, even though you change the distribution at the left and at the right end, but you just simply fixed the value of the net forces and moments. If the net force and the net moment doesn't change, okay? If both of them here still remain the same, now I can say that the solution in the interior zone are almost the same. Okay. So then if I am interested in the solution in the interior zone, I don't care about the traction here and there. I care only the net forces and moments that I show you here. Okay. So now I solve this problem by looking at the simplified BVP again. Okay. So when I check the boundary condition at the left and at the right end, I will check the satisfaction of the net force and the moments, not the traction at any particular point. Okay. Now to solve this problem, I will assume the form of the straight field again. The reason that I guess the straight field because based on the knowledge from beam theory, okay, you learned about beam theory before. So if you have the bending moment applied at the cross section, you know that based on the beam theory, if the material is linear, the distribution of stress should be linear too, right? Right? That is clear from the beam theory. So we have bending moment induced at the cross section. Stress can be obtained easily if you remember the formula mc over I or my over I, okay, from the beam theory. So I will try to start guessing the straight field based on the knowledge from beam theory. Okay. So now I guess straight field of this particular form. Okay, if you remember in beam theory, if you don't have the shear force induced at the cross section, so all the shear stresses disappear, right? So I would not have any shear stress components. So then I guess the form like this. So you can see that the shear components that I have here are zero. Okay. And how about the normal stresses? Based on the bending moment that I apply here, I apply the bending moment about x2 axis. So that will generate what? It will generate stress normal to the cross section, right? Okay, so that should be sigma 3,3. Sigma 1,1 and sigma 2,2 should be zero, right? Because we have the bending moment about about x2 axis, right? at the cross section. So that will generate sigma 33 alone. Okay, so that's why I guess the component here equal to 0. Okay, this is the information that I got from the beam theory. I don't know that the one that I guess here is correct or not. At least I start from the knowledge that I have before from beam theory. Okay, the solution of the beam from the beam theory may not be exactly the same as the solution that we got from solid mechanics. Okay. How about stress sigma 33 that is non-zero here? If you remember from beam theory, when you apply the bending moment at any cross section, you know that the variation of stress or bending stress, the variation here depends on the distance from the neutral axis, right? And for this particular case, it's simply the distance x, the coordinate x1. So based on the beam theory, stress that we got in the cross section should be a function of what? Linear function of x1, right? Right? It should be linear in x1. When you move from the neutral axis, stress increases with the distance from the neutral axis, right? For this particular problem, this should be your neutral axis, right? So the distance from the neutral axis is simply x1. So stress sigma 33 should be a linear function of x1. So that's why I guess the form like this, c multiplied by x1. And c here is simply a constant. It's an unknown constant that I don't know exactly the constant there right now. So I just simply guess the form like this. And I expect that I should be able to get C later when I try to satisfy some condition. Okay. So I start guessing stress field of this particular form based on the knowledge from beam theory. Okay. Next step, I need to confirm that the form that I guess here is correct. Okay, I didn't say that the form here have to be correct. I just guess that it should be correct. And the remaining steps, we need to check all the conditions that have to be satisfied. So if you go back to the previous lecture, again, when we start by guessing stress field, we have to check several conditions, right? We have to check the governing equation inside. The first thing that you have to check is what? You have to confirm that stress here is in equilibrium, right? Okay, before I check that condition, someone that are familiar with the beam theory, you can think about replacing C by negative M over I. Because you know that, okay, if you know the bending moment, you should get stress directly from the flexural formula, right? So we can just simply compute stress based on minus M multiplied by x1 over I. You can do it in that way as well. But I just simply keep the constant here like this. And I will get it later. But if you would like to be more specific by just simply replace C with this one, it's okay too. Okay, it depends on your experience as well. Okay. Now I start checking equilibrium conditions. So I can verify it easily for this particular case. If you take a look at, sorry, this is not right. So I think this is wrong. This is not constant. So I cannot say that the gauge stress field, because B here is 0, right? But this one is not constant. You have to change this to linear, right? This have to be linear. Okay. Now, this one is linear. How can I confirm that sigma I j comma j is 0? You have to plug it in one by one, right? But for this one, it should be clear. You can see that when you expand that term and look at sigma 3, right? That is the only one that is non-zero. So if you look at the term that we have here, okay, sigma 3 that you have here when I equal to 3 and j equal to 3. Okay, so if you take, let's say that, okay, sigma 3, if I and j are equal to 3 and j equal to 1, that is 0, right? Right? Okay, if you look at sigma 3 like this, the term that appear there have to be this, right? That the only term that involved in sigma 3, right? Because when j here is dummy index, right? So j can be 1, 2, or 3, and I just care only the term sigma 3, or you can expand the whole equation if you want to. But if you look at the term that is non-zero, so the one that is non-zero is sigma 3. So the only term that contain in the expansion is simply that one, right? Okay, that is the only term that you saw that involves sigma 3 in the equilibrium equation, and that one disappear, right? For the gauge straight field here, because sigma 3 is not a function of x3, right? Even though this sigma 3 is not constant, okay? Sigma 3 here is the linear function, but it's a function of x1. So sigma 3 that appear in the so equilibrium equation just disappear. So the remaining terms, all of them are 0, because, for example, when I equal to 1 and 2, or even for case I equal to 3 and j equal to 1 or 2, so all of them are 0, based on the thing that you guess here, because all the terms that you have here are 0. So the remaining term in the equilibrium equation are 0 automatically, and the term that is the term associated with the non-zero sigma 3 is 0, because you take derivative with respect to x3. Okay, is that clear to you? So now I can say that based on the gauge straight field, equilibrium equation is satisfied. Okay, for the problem that we look at here, the body force field is 0. So this one is satisfied automatically. Okay, is that clear to you? So just you have to fix this part. Okay. Okay, there's a question from your friend. Why don't we include the other linear term for sigma 3? That's the question from your friend. The first thing that I would like to emphasize, this is the part that I guess. Okay, so the thing that I guess here may be wrong. It depends on your experience. The reason that I put only the linear term with respect to x1, not x2 and x3, because I know from beam theory, I try to guess the solution here based on beam theory. Okay, if you look at the function that I assume here is independent of x3, because of what? If you look at all cross section that we have here, okay, you look at the cross section here, there. When you look at different cross section, you see exactly the same net moment, because you apply the moment at the left and at the right end with the same value, right? So if you take a cut at any location here, okay, you will see exactly the same moment, I think, based on equilibrium, right? So I can say that the bending moment induced at any cross section is exactly the same, equal to m. So now I expect that stress should be the same for every x3, or the dependent here you shouldn't see any x3 dependence in the gas component here. Okay, because you should see exactly the same stress for any cross section. That what I try to when I get stress field, I try to remove that dependence. How about x2? Okay, if you take a look at the bending moment that I apply here, okay, based on the beam theory, I try to base on the beam theory. I didn't say that, okay, the thing that I guess here is correct. Okay, I have to check. But based on the beam theory, this is the neutral axis, right? X2 here is the neutral axis. And if you remember, X1 and X2 that I consider here, they are principal axis, right? Right? I choose X1 and X2 to be the principal axis of the cross section. So now you apply the bending moment about one of the principal axis, right? So you apply the moment about X2. So now the stress that generated by this bending moment depends only on X1, not X2. Okay, or I can say that, okay, if you look at that line with the same distance from the neutral axis, stress that we got there at every point along that line should be the same. Okay, so what I try to tell you here that based on the beam theory, stress here should be independent of X2. Okay, is that clear? The thing that I guess here is based on the beam theory. Okay, so the dependence on X2 and X3 should be eliminated. Is that clear to you, Anne?
Yes, I think so. Yes.
Okay. Maybe you can go back and look at the beam theory. Okay. So look at the case that you can think about the case of rectangular cross section. If you apply the bending moment about that axis, what happened to the stress field? Stress field or stress component or the bending stress that you got, if you apply the moment about that axis, what happened? Stress at any location on that line with the same distance from the neutral axis are the same, right? So I can say that it will not depend on the coordinate in that direction. The same here. So the dependent on X2 should be eliminated. Okay. So that is from the beam theory. As I mentioned before, the form here I just guessed from the beam theory. It may not be right. Okay, at this point, I just try to come up with something. I just try to come up with some case form. So the simplest way that I can think about, I use the knowledge that I learned before. Okay, I have some experience in beam theory, so then I will try to start from that point. Okay, this may not be correct, but it's good start. Okay. Okay, is that clear? Anne?
Okay, yeah. Okay.
Okay. Okay. So now, when I check equilibrium equation, okay, so I can check compatibility of stress as well, right? Because we need to confirm that the gas stress field here generate displacement field. I have to check Beltrami-Michel equation, right? Okay. To confirm that the gas stress field is compatible, I just look at Beltrami-Michel equation. And because the body force field is zero, so Beltrami-Mitchell equation is simply reduced to this, right? Specific form. Okay, term on the right hand side disappear. And if you take a look at term on the left hand side, the first term and the second term, you deal with second derivative of straight components, right? Because this is the Laplace operator. And here you have comma ij. So so you can see that we have second derivative of straight component appears in Beltrami-Mitchell equation. Okay, and this one is wrong again. So I have to apologize because I simply make a copy from the previous problem. So this you have to change this to linear. Okay, because stress that we get is linear function of x. Okay, sorry. Because this one is linear, if you take second derivative of the linear function, it's always 0, right? So that term disappears and that term disappears. So now I can conclude that Beltrami-Mitchell equation are satisfied automatically. Okay? It doesn't matter the value of C is. Any value of C that you put there in the case form of the straight field, it always satisfies Beltrami-Mitchell equations, right? Okay, so what I can conclude here, based on checking equilibrium and Beltrami-Mitchell equation, I cannot get in the value of C, okay, because the two conditions are satisfied automatically. Okay, so once we confirm that Beltrami-Mitchell equation is satisfied, so now we can say that the case straight field is compatible. Or I can say that if you use straight field that you guess there to compute strain is compatible too. Okay, once strain is compatible, so now you don't need to worry about the existence of the displacement, right? You know that the displacement exists. Okay, and you know that if you look at strain displacement relationship, you can always integrate that relationship to get displacement field once strain is compatible. Okay, so now we confirm the satisfaction of equilibrium condition and Beltrami-Mitchell equation. So when we confirm this, we know that all the fields inside the body can be generated, right? Okay. The rest we need to check boundary condition, right? Okay. I will start by checking the boundary conditions at point on the side face. Okay. At every point on the side face, we need to make sure that it's traction free or stress that we get there have to generate zero stress. Zero traction at every point on the side face. Okay, so if you can confirm that, now we can say that the boundary conditions is satisfied, okay, at the side face. How can we generate traction at point on the side face? Okay, we just simply use the Cauchy formula, right? We just multiply the gauge straight field by outward unit normal vector, right? Again, because the body here is cylinder, okay, outward unit normal vector simply n1, n2, and 0. Okay, n1 and n2 here are arbitrary depending on the shape of the cross section, because I didn't make any specific assumption on the shape of the cross section, so now it can be arbitrary. Okay, n1 and n2 here can be anything depending on the geometry of the cross section. Okay, if you look at the product here, because only non-zero component we have is sigma 3,3. So when you take the product here, it's give you 0. automatically. It doesn't depend on the choice of C, right? So even you change the constant C to any value, so this equation, this condition is still satisfied, right? So T1, T2, and T3 are generated by the gauge, the gauge straight field are always zero, like this. So this implies what? The boundary condition on the surface S pi are satisfied, okay, for any value of C. Or I can say that by satisfying the boundary conditions on the surface S pi, I cannot get the value of C. Okay, is that clear to you? Okay. Now it still remains to check the boundary condition at the left and at the right end. So I look at the left end first. Okay. So now as I mentioned before, I will not try to force the boundary conditions in terms of the traction at every point. Again, I will go back to the same concept using the Saint-Bernard principle. I will try to check the net forces and net moments, okay, at the left and at the right ends. At the left end, first I have to generate traction, and then use that traction to compute net force and moment, okay? So I will use the expression that I used before. So this is the expression for the net force in terms of the straight component that we guess. Okay, we can plug it in sigma 1, 3, sigma 2, 3, and sigma 3, 3 again into this equation, right? So we know that sigma 1, 3 and sigma 2, 3 are 0 for the gas form. So that term disappear and that term disappear. How about the last term? Because sigma 3, 3 is not constant. It's linear in x1, right? So I plug that thing in. Sigma 3, 3 is simply C multiplied by x1. I plug that thing in. And then I just simply remove C out of the integral because it's constant. Now you end up with this result. The first and the second component are 0. That should be clear because you integrate 0, you get 0. Okay, how about the last one here? What can we conclude for the last component? Again, as I mentioned to you before, the origin is at the centroid of the cross section. So this integral is 0. Okay. So if you didn't shoot the origin at the centroid, this one will not be 0, right? Okay, for this case, that term is 0 because the specific choice of the origin that we have here. Now we can say that the net force is 0. All the components of the net force are 0. Okay, and that's what we want, right? Because if you look at the net force and moment at the left end, the net force is 0. Okay, so I can say that at least now at the left end, the net force conditions are satisfied, right? Because the straight field that we guess satisfies 0 net force conditions. Okay, now let's look at net moment. Okay, all the components we have here can be calculated easily by simply plugging in sigma 1, 3, sigma 2, 3, and sigma 3, 3, right? And again, because based on the gas components that we have before, that one disappear, that one disappear. And sigma 3, 3 is simply a linear function of x1. So I plug that thing in, I get something like this. I remove the constant out of the integral. So we have the integral like that. So it's clear that the third component here disappear, right? Because you multiply 0, anything with 0, you get 0. So that term disappear. you can see easily there, right? Okay, how about the first and the second term? If you remember again, x1 and x2 that we consider here, they lay along the principal axis, right? Or I can say that x1 and x2 are principal axis of the cross section. So based on the definition of the principal axis, the product inner shear have to be 0, right? Based on the principal axis property, so that term disappear. The integral here is 0. Okay. How about the second integral? The integral of I1 square, that is simply I2, right? The integral of x1 square over the cross section is simply the moment of inertia of the cross section about x2. So that is simply I2. Okay. So now I got the result like that. You can see that the gas straight field generate net moment of that particular form. The first and the third component are 0 automatically. But the second component can be non-zero, depending on the value of C, right? If C is 0, you get 0. But if C is not 0, you get a constant like that, right? So you get the product between C and I2. Now, the thing that you want to do, you try to enforce the condition at the left end. If you compare the one that you got from straight field, you can see that that one is satisfied automatically because they are exactly the same. F0L and FL are exactly the same. How about ML and M0L? Can they be the same? This one and that one? It can be the same, right? The one that you got here and the one that you got there. The one here is the one that prescribed, but the one that you got here, you got from the case straight field. They can be the same if and only if C is simply minus M over I2, right? That's the only way that you can say that ML equal to M0L. Okay. The force, the net force conditions are satisfied automatically. It doesn't matter what the value of C is. But for the net moment conditions, that condition can be satisfied if and only if C is the negative M over I2. Okay, so now I can say that if you want to satisfy the net force and moment condition at the left end, C have to be minus M over I2, or this is the way that you can use to get C. Okay, so I can get C equal to this value to make sure that the left end condition are satisfied. Okay. Do you have any question about anything here? At least we know the value of C. Because if you look at the case form of straight field, we have only one unknown constant. Now we already got that constant here. Okay? Or I can say that now we know everything in the form that we guess. We don't have any constant left to be determined. But we still have one more condition to check, right? We need to check the condition at the right end, right? So now we expect that, okay, the C that we got here by checking the boundary condition at the left end also make the condition on the right end to be satisfied. Okay? If we cannot satisfy the condition at the right end with this C, now you have problem. You have to go back again and guess the form of straight field. Okay? So now I will check the condition at the right end. Okay? I do exactly in the same way. I compute the net force due to straight field that I get 0 like this. And for the net moment, I perform the integration in the same way. Again, I can see that, okay, that term disappear because of the definition of the principal axis. And that term disappear. And that one is simply I2. So I get something like this. Okay, so now you can see that at the right end, the net force condition are satisfied automatically. But the net moment can be satisfied if C equal to negative M over I2. If you compare this one and that one, they can be the same if and only if C is simply minus M over I2. We end up with the same C. Okay, if we try to enforce the condition at the left end and the condition at the right end, we end up with the same C. That is a good news, right? Because if we end up with different C, different value of C, now you have problem because you cannot satisfy the two conditions at the same time. Okay, so the case solution will not be the solution. But in this case, we can see that to satisfy the left end condition and the right end condition, we need the same C. Okay, so this implies what? The case form that we have there should be correct, right? Should be correct. And we already got C as well to make sure that the boundary conditions are satisfied. Now, this is the conclusion. Based on the straight field that we guessed like that, we can see that it satisfies equilibrium for any value of C. It satisfies compatibility condition or Boltzmann-Michel equation for any value of C. It satisfies the conditions on the side face for any value of C. It satisfies the simplified boundary condition at the left end if C equal to minus M over I2. And satisfy the boundary condition at the right end if C equal to minus M over I2. So now we can say that straight field sigma that we guess is the solution of the simplified problem if C is minus M over I2. Okay, so now I can say that this is the solution that we would like to get. Right? That is the final solution of the simplified BVP. I would like to emphasize that the solution that I got here is the solution of the simplified BVP, not the original BVP, because we just simply enforce the net force moment condition at both ends, not the original condition involving traction. Okay, is that clear to you? Now we're done with the guessing. We're done with getting straight field by guessing the form, okay, and checking all the conditions. The next step, we need to get the remaining fields, right? And that should be simple. Now, before I forgot, you can see that this kind of problem, we get exactly the same solution as the beam theory, okay, or the beam theory yield the same solution as what we have here, okay. Now we have to get strain field and displacement field. Strain field can be obtained easily, plugging in this formula again. Okay, based on the strain that you got, plug it in, you get strain like this. So you have only normal strain, no shear components because we don't have shear stress anyway. Okay, displacement field we can get as well. Okay, based on the integration of this strain displacement relationship, you don't need to worry about the integration because I shouldn't say that. You don't need to worry about the existence of the displacement field. Okay, so the displacement field can be obtained by simply performing the integration. The process is quite tedious, right? Because you need to deal with 6 independent equations. You have to follow the same procedure again as what you did in your homework. Okay, I didn't show you the detail here because the procedure is exactly the same. Okay, so you perform the integration, but you don't need to worry about the existence of the displacement because you already confirm Beltrami-Michel equation, right? Because stress that we get at the beginning satisfy that equation. Okay, so now strain that we got here is compatible. So when you plug it in here, you can always get the displacement field by performing the integration. So this is the result that you got from the integration. Again, here, I separate the displacement field into two parts. The first part is unique, and the part that generates the strain here. So I can say that the part that is unique here, because it's unique in the sense that there is no constant left there. So that the displacement corresponds to this strain. But the one here we call the rigid body part. Okay, the rigid body part will not generate any strain, or it generates zero strain. Okay, that we call the rigid body motion. And that part, you have a lot of unknown constants. So basically, you have 6 of them, and that represent the rigid body rotation and rigid body translation. Okay, we cannot get all of them here for this particular case because rigid body motion is still there. We didn't restrain the body against rigid body movement. We only specify traction condition at the boundaries. Okay, so I will leave the displacement field like that. Okay, so I can say that this particular problem, we have non-unique displacement field. But if you don't care, like I told you before, if you don't care about rigid body motion because that generate nothing, the displacement field generates zero strain. This part generates zero strain and zero stress. If you don't care about that part, you care about the one that generates strain and stress. So now we can say that that part is unique. Okay. Okay, I have remarks here as well for this particular problem. If you look at stress field that you got there, and then you try to generate a traction at the ends, you would like to know what kind of traction you have to apply at both ends to get the exact solution. Okay, because the one that I solve here, I just try to simplify the boundary condition at both ends. I try to satisfy the simplified boundary condition at both ends. I would like to know straight I got there is the exact solution of any problem or any kind of traction that I have to apply at both ends, and straight I got before it's the exact solution. So now I start to generate the traction from stress I got before. So I simply multiply stress that I got by our unit normal vector at the left end. I get something like this. Okay, you can see that traction that I have to apply at the left end have to take this particular form. So I need to apply traction in x3 direction as a linear function of x1, like this. Okay. The same thing for TR. I need to apply the traction at the right end in this form. Once I apply the traction at both ends of this particular form, now I can say what? I can say that the solution that I got before is the exact solution. Okay, is the exact solution for exact solution in the sense that it can be a solution at every point of the body. Okay, or I can say that the simplified or the original boundary value problem are identical for that special case. But if you apply T0L and T0R, not exactly the same as TL and TR, but the net force and moment are like this. Now I can say that stress that I got before is simply the approximation, okay, of the original problem. It's simply the approximate straight field of the original problem. And that approximation is very good if you just simply look at the solution in the interior zone. You know what I mean, right? So if you don't care much about the solution at the end zone, stress that I got here, or the strain and displacement that I mentioned before, are the good approximation in this region. Okay. Is that clear to you? Okay. I will stop here. I will come back and talk about the third problem next time. Before I leave the class, I would like to give you the information on the quiz tomorrow. Okay, so I changed my mind. Before I told you that okay, the exam is going to be the closed book exam. So I think because it's an online exam, it's very difficult for me to control anything. So I will allow you guys to open the book. Okay, you can open the note and the book. Okay, so I will change from the closed book to the open book exam. Okay, you can bring any book, any notes. Okay. I will start the exam about 9 a.m. in the morning. So you're supposed to log in into Zoom about 10 or 15 minutes before the exam. Okay, I will give you the link of the Zoom in my course field. Okay, you can get that information and log in into the Zoom 10 or 15 minutes before. I think the procedure of the exam Dr. Thirapong gave you before, right? I will try to follow the same procedure. So basically, I will show you the exam one by one. I will not give you the whole exam at the same time. I will show you the exam problem one by one. Once you're done with the first problem, you have to submit the solution. The way to submit the solution, you have to submit it online based on my course view. You have to submit your exam solution in my course view. Okay, if you don't, I think you should be familiar with that submission procedure, right? Because you submit your homework. So I will try to create the assignment box in my course view, and you have to submit that in the system, your solution in the system. Okay, for each exam problem, I will tell you exactly the time that I gave you, and also one is done. Okay, I will allow you to take the photo of your exam solution and try to submit in the system. Okay, I may give you 3 minutes for taking the picture of your exam solution and submit into the system. Okay, if you are not familiar with that procedure, why don't you go back and practice? Okay, I will give you limited time on submission of your solution for each problem, approximately 3 minutes. Okay, for each problem. Okay, and please practice how to convert the file into PDF. I prefer you to submit the file in the PDF format. Let's say that okay, if you have more than one page, okay, in your solution, try to find a way to combine all the pages that you have into a single file in PDF. Okay, and when you try to submit your file, change the name, okay, or put the name of the file starting with your ID and put your first name after that. That should be enough. Okay, name the file, use the student ID following by your first name. Okay, that should be enough. and I will not allow you to do the exam in iPad or in any application. Just write down your answer in the paper, okay? In the paper, and take the picture of that paper, okay? And submit into the system, okay? You are not allowed to write or to do your exam using iPad or any applications. Is that clear? Also, the setup of your camera have to be clear. I can see you clearly. You have to turn on the video all the time during the exam. Okay, so you have to set up your camera and to allow me to see everything on your desk. Okay, the telephone or any application are not allowed during the exam, except at the time that you try to submit your your solution to the system. I will allow you to use the phone at that time, but during the exam you are not allowed to use the phone. Okay, is that clear to you?
Azan, how long we take the exam, Azan?
I am not sure yet, but I think you will take less than 3 hours. Okay, I will assign you several problems. Okay, but I will give you the time. I will tell you the exact time that you need to spend for each problem. I will give the exam problem one by one. Okay, so don't worry about that. I will provide you enough time for each problem. Okay. Any question about anything here?มีคำถามอะไรไหมครับ เกี่ยวกับการสอบ
เนื้อหานี้ต้องปริ้นมาใช่ไหมครับไม่ให้เปิด
แล้วแต่คุณเลยครับ
เปิดใน iPad ได้ป่ะครับ
เปิด iPad ไม่ได้ครับ
โอเคครับ
คือไม่อนุญาตให้เปิด iPad ถ้าทำใน iPad ถ้าคุณจะเปิดในคอมได้แต่คุณต้องโชว์ให้ผมเห็นหน้าจอคุณด้วยไงเพราะเวลาคุณตั้งกล้องเนี่ยคุณจะต้องตั้งกล้องเยื้องข้างหลังนิดนึงให้ผมเห็นบนโต๊ะแล้วก็ที่หน้าจอคุณแล้วคุณจะเปิดหน้าจอเพราะคุณจะต้องเปิดหน้าจอซูมอยู่แล้วเพราะเดี๋ยวผมจะโชว์ข้อสอบผ่านทางซูมผมจะไม่ส่งข้อสอบให้กับคุณส่วนตัวหรือทางไลน์ไม่มีนะครับผมจะเปิดหน้าจอขึ้นมา I will show the way to give you the exam problem. I will show the problem via Zoom. Okay, so you will not get the file of the exam. So I will show the exam problem on the screen via Zoom. Okay, you can read the exam problem on the screen. Okay, so you are not supposed to use any application. The iPad is not allowed. Except that okay, if you use iPad to to connect Zoom and you have to be able to show me the screen of your iPad all the time because to make sure that okay you will not contact your friend via any application. Okay, is that clear?
How many problem in the exam?
I am not sure yet.
Yeah.
Okay, but the number of exam problem shouldn't be any problem, right? Like I told you, I will give you enough time for each problem. I will not give all the problem at the same time. I will give you one by one. The first problem is done, you have to submit your solution, and it's done for that problem. And I will share you the second problem. I will do like this until we're done with the whole exam. Okay?
Yeah.
มีใครมีคำถามอะไรเพิ่มเติมไหมที่ถามมาว่าสามารถนำชีทเข้ากี่แผ่นก็ได้ใช่ไหมครับนี่คืออะไรชีทอะไรนะภัทรเดชผมไม่เข้าใจว่าไอ้ชีทที่คุณบอกจะเข้ากี่แผ่นนี่คืออะไรนะภัทรเดชอยู่ป่ะครับคือผมรบกวนด้วยนะครับพรุ่งนี้เนี่ย ทุกคนจะต้องสามารถติดต่อสื่อสารกับผมได้ทางไมโครโฟนนะครับคือไม่งั้นมันจะมีปัญหาเพราะคุณใช้วิธีการพิมพ์ตลอดเลยอ่ะคือถ้าเกิดไม่มีไมโครโฟนก็ต้องหาวิธีการที่จะติดตั้งไมโครโฟนให้ได้เนาะจะได้ติดต่อสื่อสารกันได้แบบเรียลไทม์นิดนึงได้ไหมพัฒนาเดชได้ปะพรุ่งนี้ติดตั้งไมโครโฟนให้เรียบร้อยนะโน้ตเอาเข้ากี่แผ่นก็ได้เอาได้หมดครับโน้ตคุณจะเอาโน้ตเอาการบ้านอะไรก็แล้วแต่ที่คุณทำไว้คุณจะเอาเข้าอะไรเอกสารผมบอกแล้ว Open Book คุณเอาเข้าได้แต่ว่าถ้าคุณจะเปิดเอกสารผ่านทางหน้าจอผ่านทางไฟล์คุณต้องโชว์หน้าจอให้ผมเห็นตลอดเวลาอยู่แล้วนะครับเพราะฉะนั้นไม่อนุญาตให้คุณแบบเอา iPad ไปนั่งดูโดยที่ผมไม่เห็นหน้าจอ iPad คุณไม่ได้นะครับถ้าเกิดสมมติว่าคุณไม่อยากจะให้มีปัญหาก็ปริ้นออกมาแล้วก็ดูจากไอ้กระดาษนั้นได้ผมป้องกันการทุจริตโดยการที่คุณส่งติดต่อกับเพื่อนคุณผ่านทางไลน์ผ่านทางอะไรทางหน้าต่างเนี่ยเพราะฉะนั้นมือถือไม่อนุญาตให้ใช้ถ้าคุณจะใช้ในการ Connect Zoom คุณต้องโชว์ให้ผมเห็นหน้าจอมือถือให้ชัดเจนไม่งั้นจะมีปัญหานะครับถ้าเกิดคุณกังวลก็ปริ้นออกมาเลยครับปริ้นออกมาก็ง่ายกว่าอยู่แล้วแต่ถ้าเกิดคุณบอกว่ามันเยอะคุณไม่อยากปริ้นคุณอยากจะอ่านจากหน้าจอคุณก็ต้องโชว์ให้ผมเห็นหน้าจอตลอดเวลานะครับตรงนี้ชัดเจนเนาะก็การเขียนคำตอบไม่อนุญาตให้เขียนใน iPad นะครับไม่อนุญาตให้เขียนด้วยแอปพลิเคชันอะไรทั้งสิ้นคุณจะต้องเขียนลงในกระดาษ A4 ก็ได้นะครับที่เตรียมมาเขียนในกระดาษแล้วก็ส่งโดยการถ่ายรูปเท่านั้นนะครับปากกาให้ใช้สีน้ำเงินนะครับไม่ใช้สีดำนะโอเค I forgot to tell you for the pen that you need to use in writing your solution you have to use the blue one okay the blue pen okay you are not allowed to use any the other color like the black one okay use the blue one okay do you have any question about anything about the procedure that I just mentioned to you any question or is there anything that is not clear to you basically the procedure should be the same as what Ajahn Thirapong used before for the quiz and for the midterm exam I think he used to send you the procedure right how to set up the camera ready for the exam okay so I suggest you to log in into the Zoom 10 or 15 minutes before the exam
ใช้ดินสอได้ปะครับ
ไม่ได้ครับใช้ดินสอไม่ได้ครับต้องใช้ปากกาเท่านั้นครับ you are not allowed to use pencil okay you have to use pen just in case that you try to do something with you change your solution at the last minute when you try to submit your answer okay if you use pencil you can erase things that you write there easily and you change your answer easily so you are not allowed to use pencil okay and when you try to scan you try to take the picture of your solution you can make it in color right คุณสแกนไม่ต้องเป็นขาวดำก็ได้นี่ใช่ไหมก็ทำเป็นสีดิผมเชื่อว่าทำได้นะใช่ไหมทรงกฎคุณทำเป็นสีได้ไหมงั้นผมอยากให้คุณทำเขียนเป็นปากกาสีน้ำเงินแล้วใช้ปากกาเท่านั้นห้ามใช้ดินสอนะครับเพื่อป้องกันการทุจริตอะไรทุกอย่างที่ผมเท่าที่ผมคิดออกนะครับก็ใช้ปากกาสีน้ำเงินถ่ายรูปเป็นสีครับก็ไปฝึกถ้าเกิดคุณยังทำไม่เป็นก็ทำให้มันเป็นสีออกมาผมเชื่อว่าทำได้นะใช่ไหมทำได้อยู่แล้วเพราะว่าผมก็เคยให้เด็กสอบแบบนี้มาในหลายครั้งแล้วก็ไม่เห็นมีปัญหาอะไรนะครับถ้ายังทำไม่เป็นก็ไปฝึกครับเรายังมีเวลาการสอบเนี่ยผมจะให้เวลาผมจะบอกเวลาชัดเจนนะครับแล้วเวลาส่งข้อสอบเนี่ยผมก็จะบอกคุณชัดเจนว่ามีเวลาเท่านี้นะปกติแล้วเวลาส่งข้อสอบแต่ละข้อผมให้เวลาไม่เกิน3 นาทีใครส่งเกินก็ไม่รับไม่ใช่ไม่รับหรอกส่งเกินก็คะแนนข้อนั้นก็0ไปนะครับ นะเพราะเชื่อว่า3 นาทีนี้เหลือเฟือเพราะว่าผมไม่ได้ให้คุณถ่ายรูปทั้งหมดทุกข้อพร้อมกันนี่ใช่ไหมผมถามคุณทีละข้อเนี่ย1 ข้อเนี่ยอาจจะแค่หน้าเดียวหรือ2 หน้ามากสุดเนี่ยผมว่าไม่มีใครทำ10 หน้าแน่ๆใน1 ข้อเนี่ยเพราะผมจะแบ่งเป็นข้อย่อยๆเพราะฉะนั้นโอกาสที่ต้องถ่ายรูปหลายๆหน้าแล้วก็ส่งรวมไฟล์เป็นไฟล์เดียวแล้วส่งเนี่ยมันไม่เสียเวลานาทีเดียวก็เสร็จแล้วถ้าคุณบอกหมดเวลาแล้วคุณทำเลยคุณถ่ายรูปเลยยังไงก็ทันนะครับเพราะฉะนั้นใครส่งเกินเวลาไม่คิดคะแนนนะครับโอเคI will give you I will tell you the time that you have for submitting your solution if you cannot submit your solution in time you will not get the credit for that problem okay so I will give you approximately 3 minutes to submit your solution if you cannot submit that in time you cannot get the score for that problem okay and you cannot submit your solution before I will tell you when you can submit okay I will give you the time for doing the problem and then once you are run out of time I said okay stop now you can start taking picture and get the file and submit to the system okay and during the exam you are not allowed to go to the restroom but anyway I will have a break for you during the exam so I will tell you okay now you can go to the restroom for example okay นะผมจะมีเวลาให้ไม่ต้องกังวลนะครับเพราะว่ากระบวนการสอบเนี่ยคุณน่าจะคุ้นเคยดีจากวิชาอื่นด้วยเหมือนกันนะครับนะระหว่างทำข้อสอบก็จะไม่อนุญาตให้ลุกเข้าไปเข้าห้องน้ำไม่มีนะครับแล้วก็ถ้าจะเข้าห้องน้ำเดี๋ยวก็จะเข้าตอนเบรกผมจะมีเวลาเบรกให้นะครับโอเคนะครับ
อาจารย์คะถ้าสมมุติว่าทำเสร็จแล้วก็ถ่ายรูปก่อนเวลาที่อาจารย์ให้3
ไม่ได้ครับไม่ได้ครับไม่ได้ครับทำไมต้องถ่ายรูปก่อนนะคือถ้าเกิดใครทำอะไรก่อนแบบนั้นเนี่ยก็ถือว่าทุจริตครับเพราะว่าคุณห้ามแตะมือถือถ้ายังไม่หมดเวลา you cannot take the photo before you are run out of time okay so let's say that okay if I say that okay this problem I give you 10 minutes if you can solve the problem you spend less than 10 minutes you have to wait until I say that okay now is the time for you to submit your answer you cannot do anything you cannot take the picture okay before I tell you that you can do it okay โอเคไหมครับผมจะไม่อนุญาตให้ใช้มือถือนะครับหรือเครื่องมือสื่อสารใดๆระหว่างที่ยังไม่หมดเวลาสอบห้ามถ่ายรูประหว่างก่อนหมดเวลาสอบเพราะว่าผมกังวลว่าถ้าเกิดคุณถ่ายรูปก่อนแล้วคุณส่งให้เพื่อนคุณผมก็เช็คยากนะครับเพราะฉะนั้นห้ามนะผมจะดูจากหน้าจอเนี่ยเพราะว่าผมจะเปิดหน้าจอแล้วผมจะเรคคอร์ดไว้ตลอดเวลาอยู่แล้วนะครับ so I will record the video during the exam so if there is something that I doubt about you know something wrong happened during the exam I will try to investigate that later okay so ผมจะบันทึกนะครับการสอบไว้ตลอดเวลานะดูหน้าจอคุณได้ตลอดเวลาเพราะฉะนั้นทุกคนจะต้องเปิดกล้องตลอดเวลาด้วยนะครับนะแล้วก็การตั้งกล้องต้องให้ผมเห็นหน้าจอนะครับถ้าคุณจะใช้หน้าจอคอมและถ้าคุณใช้หน้าจอมือถือก็ต้องให้ผมเห็นหน้าจออยู่ตลอดเวลาแล้วก็ที่สำคัญคือถ้าเกิดคุณใช้คอมก็มือถือเนี่ยไม่ควรจะเปิดไปเปิดมาแบบจะถ่ายรูปอะไรเงี้ยไม่อนุญาตนะถ้าเห็นใช้แอปพลิเคชันเมื่อไหร่นี่ถือว่าทุจริตทันทีครับไลน์อะไรเงี้ยห้ามใช้โอเคนะครับมีคำถามอะไรเพิ่มเติมไหม Do you have any question about anything don't worry much even though I change from closed book to open book I will not adjust the level of difficulty of the exam problem. It's still the same because I just want to make sure that okay you can access to any formula, any equations, okay? Because several of your friends just show me about that concern because they just said okay they cannot remember all the formulas, so they worry about that, so don't worry now. So I will allow you to open the book. Okay. But if you don't understand the material before you go to the exam, I think that cause some problem, because if you try to figure it out, the formula or the expression that you have to use in the exam, you will not have enough time. Okay, understand that, the material clearly and the step that you should do when you got the problem, that should be clear already. Okay, don't try to study the material during the exam, because the time that they gave you appropriate for each exam problem. Okay, and one more thing, you are not allowed to submit your exam solution twice. Okay, so I will use the first version that you submit. Okay, so I will try to lock the system that allow you to submit only one time. Okay, once you submit, it's done. Because if you can think about, if we organize the exam on site, you don't have the second chance. Whenever you turn in your exam solution, it's done. Okay, นะเวลาส่งข้อสอบเนี่ยส่งได้ครั้งเดียวเนาะเดี๋ยวผมจะพยายามไปล็อกระบบเอาไว้นะถ้าใครส่งแล้วก็ส่งเลยไม่อนุญาตให้ส่ง2 ครั้งถ้าเกิดสมมุติผมไม่ได้ล็อกระบบใครส่ง2 ครั้งผมก็จะเอาครั้งแรกเป็นหลักนะครับเพราะฉะนั้นก่อนส่งเนี่ยดูดีๆก่อนโอเคนะครับ Okay, so if you don't have any more questions or you don't have any concern about anything, I will stop here. Okay, I will see you guys again tomorrow. Okay, I will try to provide the link to you before maybe 15 minutes before. Okay, you can enter the room and then try to set up the environment to fit with the the rule or the procedure that Ajahn Chirapong mentioned in before. Okay.